This is Dr. Anthony Revis with Introductory Concepts in Polymer Chemistry by Dr. Anthony Revis, Chapter 8, Manufacturing Highlights. In this chapter, we will review just a few manufacturing highlights and features to help get a broader picture of just what it looks like when these polymers are being produced and where they're used and why they're used that way. But this is not an exhaustive chapter by any means. It's an overview to expose you to the concept of what happens in manufacturing. Let's talk about the raw materials and end products. Manufacturing of polymers uses raw materials for products that have distinct physical and chemical properties. In other words, they take these raw materials and they transform it into some useful product based upon some distinct physical properties and some distinct or unique chemical properties. The polymer products are typically lightweight, and that's one of the features of a polymer over some other materials such as metals. Polymers are lightweight. In fact, that's why polymers are used in a lot of applications, because it reduces the weight. For example, in a vehicle, using plastics, polymers over metals decrease the weight of the automobile, and thereby giving it better fuel economy. In other words, the engine doesn't have to pull around a lot of dead weight, so it can carry around the lightweight polymers. So they're typically lightweight, but they can be hard. They can be very strong. Polymers can be brittle. They can be tough, and they can be flexible. And we've already examined in this course the mechanical properties that lead to these particular features. And those mechanical properties are based upon the polymer compositions. So we've talked about that already. Now, the polymer can be the end product. That can be the final result. You make the polymer, that's it, and that's what's sold to a customer, to your household, to grandma. Or it can be an ingredient in another product, and that is where a lot of polymer is consumed. Many of the polymers that are made are often not used exactly as that polymer as it comes out of the pipes at the plant, but it's transformed a bit further into an exact product. Some polymers are manufactured with special thermal, electrical, and optical characteristics, for example, or to name a few features. And there are many other reasons why we manufacture polymers, and there are many other features these polymers can have. Manufactured polymers are used in communication devices, furniture, packaging, transportation, fabrics, aircrafts, cleaning supplies, insulation, and many more consumer applications. So there's a host of applications for polymers, for plastics in the world. Okay? So again, polymers have a wide range of applications in consumer products. If you look around your home, you'll see them. You can't escape it, frankly. Polymers are used extensively across many industries. We'd like to highlight an example of a leader that's used, polypropylene, as a way of showing you how it's used in industry, and we'll show you how this one's manufactured. So let's talk about polypropylene as an example of what the polymer industry looks like and how it makes these polymers and how it thinks about them. Polypropylene is processed in film for packaging and in fibers for carpets and clothing. So in the film form, it has one application. In the fibers, it has another. As a bead, it might have another. As a bulk material, it might have another property. Polypropylene and many other polymers fill a wide range of needs because of their ability to manipulate their forms, their shapes, based upon their physical properties. It is also used for injection molding articles ranging from car bumpers to bowls, and can be extruded into pipe as well. So you'll have these bowls and plastic bowls. Many of the plastic bowls you have are polypropylene. Okay, Bottle caps is another use of polypropylene, so really large use. Many of the bottles will be PET, and the caps will be polypropylene. If you consider the industries where polypropylene are used, or at least the market applications where they're used, we show you this pie chart here where there's film, rigid packaging, consumer products, technical parts, and textiles. So these are different areas where they're used. You see packaging's the leader at about 28%, and it's followed by technical parts, basically those parts that you need to make something work, dashboards, switch and drain pipes, electrical cables and things of that nature. Then just a host of consumer products. Films real large, particularly in food packaging, and then textiles for carpets and carpet backing. Not only the carpet, but the carpet backings will use polypropylene. So this is the example. This polymer is an example that's typical of other polymers in the industry. They all have this range of applications. Most of them have 3 or more applications. Very few have just simply one application anymore. Okay, they all have several applications, and they're well defined. Let's take a look at the manufacturing plant for polypropylene. It's basically, this is a schematic of what the polypropylene plant will look like if we were manufacturing it. We start on the left side of this diagram on this plant. There's a pumping meter, and above the pumping meter is a catalyst adder. The cat adder does exactly what it says. It adds the catalyst, and if you walk around a plant and you're out on a manufacturing site, you'll hear the guys talk about the cat adder, and you'll hear these terms, the meter pump, and a lot of short names and terms for it. And what happens is cat adder is connected to a fluidized bed reactor. And it's called a fluidized bed reactor because the material in there is kind of in a fluid state. So it's not just sitting on the bottom stirring, it's really filling that vessel. And that's why it's called fluidized. All the particles and everything in it are in a somewhat fluid state. And you have when this process through, it passes over, will go to the right side. Once it processes, passes over to a polymer, where the polymer and unreacted material go, and that's called a separator. So the material goes to a separator, and it takes out the unreacted propene, is recovered, recycled back, drop the polypropylene out the bottom. That goes to a silo for holding, to do other things with. But the other part that happens is the unreacted gases that are in here, and you'll see what those are. They're compressed back, sent through a heat exchanger, reclaimed and recycled. And so this is kind of the loop for this process. Okay, and you also have a port where you have a propene and the comonomer feed, and that's important. So you have the propene and a comonomer feed that comes in the bottom, and it goes into the fluidized bed where the catalyst is. It's all in a fluid state. It's swirled around in there. It reacts in the fluidized bed and is sent out again to the separator, drop out the polymer at the bottom, and reclaim gases at the top. So this is a general schematic of what you might see. There are a few more bells and whistles on them, but for the most part, many of the polymer processes will boil down to looking something like this. It'll have a cat adder. It'll have a metering pump. It'll have a port for adding in the monomer and whatever gases that monomer is going to be polymerized in the presence of. It'll have a place to drop out the polymer, reclaim the gases, and a heat exchanger. In terms of how this is processed, let's just take a look. There's 4 broad unit operations that happens in the manufacturing of this. The first unit operation is a propene hydrogen gas, and typically you'll have the polymer in some gas. In this case, it's hydrogen gas. Mixture is passed over the Ziegler-Natta catalyst at about 50 to 90 degrees C and a pressure of about 35 atm. So that's what happens in this first part of the plant in this particular unit operation here. So basically, again, this is the load station and the reaction. So we load it and react it. And we load it based on concentrations of the propene needed, diluted diluted in the hydrogen gas. And if you have comonomers, you put it in. So any other of the polymers that we've talked about in this course will probably be made very similar to this. Second unit operation is the polymer separated from propene and hydrogen using a cyclone. And so it'll drop in a cyclone. The cyclone basically, exactly what it does is a cyclone. It spins basically. It pushes the propene out the top, drops the polymer at the bottom. Okay, so basically it's like a big centrifuge, if you will. So the polymer drops down to the bottom, and all the unreacted gases get recycled. Then the separator, the catalyst remains in the product and is destroyed using water or alcohol for polypropylene, and that's typical. So this is where it's quenched. Everything's quenched here. We call it a quenching step. We talked earlier about when we carry out this reaction, you have the initiation, you have a propagation, and you have termination. Termination also involves quenching the catalyst, so it's not reactive anymore. Okay, and now some catalysts actually will be what's called supported catalysts. They won't be what's called soluble in the fluidized bed. They'll be on stationary. So there are also processes like that exist in industry. But we thought this would be a good example to show you kind of overall what they look like. The fourth unit operation then is the polymer is converted into pellets and packaged. So once it gets to the silo sends it off. It goes off the silo on trucks or what have you, and then it's cut into pellets, and now it's ready to be further manufactured for a product or put in other products. And this would be typical again for most of the polymers that we've talked about, particularly chain polymerization. So this would be typical of the chain polymerization processes. The condensation polymerization processes are a little bit different, but it involves many of the same types of steps. About 4 major operations that go on, and most of these polymers will get you to a finished material. Okay? So now that you have this polymer, this plastic, what do you do to transform it into something that's useful? These next slides will show you that. It will show you the types of equipment and that's used to basically turn the polymer into a finished product that a consumer can use, or an intermediate product that will go into another application, then off to the consumer. In this case, we show you an example. It's called compression and transfer molding. In compression and transfer molding, it's simply a stamp. So it has a mold. The mold's been made, and each device will have a mold. And mold making, by the way, tends to be an expensive part of the proposition, because this is one of the costs that manufacturers have to pay for the mold, and then you pay for the cost of making the material. So the manufacturer will own the molds, and some molds will be very unique for that particular product and for that application. And so there are many, many molds. So you would go into a shop like this, and you have rooms of molds. Perhaps one room will be dedicated to this type of material or to that manufacturer or what have you. And so you have the molds. They pop in the mold, and basically they stamp it in to this part, and they use heat to basically melt the polymer. They stamp it into this. The polymer hardens, and you have trays, bowls, dishes, whatever part comes out of it. So this is one example here of the way it would be. You have the heat and cooling happening. You have the base of the mold, and you have this hydraulic pump, and it just all presses it together, and you get the product. Again, that's compression and transfer molding. It basically transferred the shape of the mold to the plastic. Another process that's used is injection molding, and this is used for thermoplastics and thermosets both. And oftentimes for these, you'll make some products, but many times what's made is you'll just simply make the pellets. So again, oftentimes you will make rope type products from this injection mold, but many times this is a way of making the pellets and putting them in the form that the customer might take, and then they would use that thermoplastic or thermoset for making their own product. And so you started with the feed hopper of the polymer, and that's the polymer that was stored in the silo. It basically hydraulic pressure rams it through. then you have the spreader, and you have this nozzle, and you have a mold and a mold cavity, and there you go again. You get a product based upon that mold, or you simply might send it through and get some pellets in a different form. So it just really depends on what you want. You get that product based upon the mold and the mold cavity. Okay. Another process that's used is shown here. This is another way of extruding the plastics, and in this case, you're going to extrude it as a pipe, or as a part, or as a sheet. We show you here a couple of examples of pipes and parts. And so in this case, similar processes that you've seen before in these other two designs. You have a feed hopper, and you have these turn screws, and a turn screw does exactly what it says, it turns screws. Then along the path, you have these heaters. You have this molten plastic that it's occurring inside this device, and as it goes through, it is extruded as the final product. Okay, and that's what you get. And again, all of this is based upon design. There's a fair amount of shaping of the die. You have a die shaper there, and that's all again engineered by machinists. And you get this nice part. You get your pipes out, or you get whatever parts you want. And yet another form is what's called a brown film extrusion process. This is basic for making sheets, making bags, films, and sheets. Okay, so you make some bags, you make some film, you make some sheets. That's what happens on this particular device, and it's much like the others. You basically will have your heaters, your extruder, your tubing die, again, helps you make or form tubing, and your shapes or the film, and you basically pass it through. You have air in there to help with the film, with the forming of the film, the shapes. You have a pinch roll, guide roll, goes over, the air bubble come out, and voila, presses down to a nice sheet of film that you can wrap your sandwich in. Okay, so that's how we would do those. All right. So there you have it. That's 4 ways that you would envision making polymers, and most of the polymers that we talked about, many of them will be done this way. So let's finish up then by talking about green chemistry. Green chemistry. Polymer science merged traditional polymer chemistry and green chemistry in the development of environmentally responsible products and processes. In other words, green chemistry means that the chemistry is thinking about the environmental impact as part of its plan. So in planning the polymer, in planning the manufacturing, how it would interact with the environment or impact the environment is part of the process, part of the plan. Okay, this includes green packaging, photodegradable plastics, edible food wrappings, which is pretty cool. It also looks for ways to use as little packaging as possible to reduce waste. And packaging, again, with the amount of things that are shipped, is a huge industry for plastics, but it's also a huge waste for plastics. So what industry thinks about, or in most industry today is almost mandated to think about, is what's called cradle-to-cradle recycling. In other words, cradle-to-cradle recycling involves a never-ending loop from the use of one product that dovetails to another possible use through recycling. So it's thought about, if I make this plastic, where might I, when this plastic is done, where might I send this plastic or recommend this plastic or have an agreement with some of the companies say, once the consumers have used this plastic, it's reclaimed and you're going to use it to make bumpers or use it in highway construction or what have you, because plastics are used in asphalt, for example, and they call it plashphalt, is an example of a use of plastic. So you think about it, you have the recyclables, you have the products, you have the consumers, and how do the 3 large areas work together to make sure that handling of the polymers is done in an environmentally responsible way, which we call green chemistry. So when we think of green chemistry, we think of recycling. There are these 4 R's that we like to talk about or we think about. One of the R's that in dealing with green and recycling is to reduce. Reduce the amount of material used. For instance, use less plastic in the production of a bottle. So to use less plastic, perhaps we can make the polymers tougher so we can make them thinner. So we use less in there. Perhaps we will make the sandwich bags thinner. For example, most plastic bags don't need much over 6 hours of time in the bag. At best, it might go 24 hours. Therefore, it doesn't need to be as thick to avoid air staling from the air. So perhaps you make the plastic bags a little thinner, use a little less material. Those are just examples. Or you make the toys a little thinner, or what have you. Then the other is reuse materials. For instance, use your own bags at the grocery store. Great way to do it. Another example, okay, would be to basically, you already receive 1 plastic bag on Monday. If you're going back to the supermarket on Wednesday, take that bag back to the supermarket with you to collect your groceries in, or what have you. Okay? The other is recycle materials. That is, don't throw beverage bottles away. Recycle. Recycling really does help save the environment. It is a very important aspect of being environmentally responsible or going green. So recycling really does help. So be sure you segregate your materials for your recycling days in your community. Then the other is recover. Recover either the materials or the energy content from the materials that cannot be recycled. Now, for instance, burn unused plastics that contain high energy content. Now, that one is a challenging one because while it sounds like a noble idea and a wonderful idea, many of the plastics don't have that high of BTU. But there may be some unique applications where the BTU produced from them is sufficient for that operation. Okay? So there you have it, the 4 R's. This is how we think about being environmentally responsible. Okay? Now, when it comes to recycling, all plastics have a recycling code. We show you those recycling codes here. And so recycling plastics are sorted by these codes. In fact, it's recommended that you sort them at home by this, or find out how your community sorts the plastic. Because, for example, if you contaminate a load of plastic with a material that's non-compatible with it, oftentimes those loads have to be sent to the landfill and not reused. So you want to pay attention to the codes. We won't go into them in any detail here, except to say that each has its code. PET is 1, HDPE 2, PVC 3, LDPE 4, PP 5, polystyrene 6. They each have their own unique codes. We take a look at those codes, okay, and decide how we recycle. It is worth noting that PVC is a polymer that you want to pay particular attention to because it contains chlorine. Chlorine plastics have to be segregated into chlorine-only areas, okay? Because they cannot be reused as many other plastics, and burning of them creates chlorine gases, which could also be harmful to our environment. So be aware of the recycling codes. They're printed on all plastics. If they're not printed, you can simply Google them, and you Google them with your smartphone, and you'll get the answer right away, okay? So be aware of it. You want to think about this being environmentally responsible by recycling. Another way to be environmentally responsible is to look to use renewable resources. That is, materials, raw materials that come from nature and can go back to nature. Okay? Here we just highlight some examples here. We really wouldn't expect you to memorize these, but just to highlight that there are some major automotive manufacturers who are doing some work in this area to make their products, that vehicle you drive in, more environmentally responsible, to make it into a greener product. You see examples where indoor panels are being used with certain materials. Okay? And we show you the feedstock of these, and these are feedstock that are renewable, unlike polypropylene, which comes from fossil fuel. So these will come. You look, the indoor panels, both Chrysler and BMW are looking at those areas. Door panels are a very good application because you can use it there, and it can help with insulation and things of that nature. Then you have seating headrests. Examples there, Lincoln's and Ford Lincoln's looking at that. Fuel lines, which is pretty ambitious undertaking. That's a really ambitious undertaking by Fiat. Then you have Nissan looking at floor mats, and then Toyota radiators, in tanks, and these again are looking at where polymers might be used in these applications. Pretty ambitious, and you see it's percent bio-based, and so really you want to get that. If you note this, 70 down to about 40%. And key here is that it might not be always possible to get it 100% bio-based, but the more we add bio-based to it, the better it helps our environment, because fossil fuels is not a renewable resource. At some point, it will not be available. Let's take a look at, finally here, at some pretty innovative technology that's helping with going green and with being more environmentally responsible, using less polymer, being more efficient with the use of the polymer, and more specific with the use of polymer, and reducing the amount of trim from polymers. One of the things that happens when we didn't talk about it, but earlier when we showed those manufacturing processes, many of them will have trim processes as well, where you trim off polymer, and that's basically waste polymer. 3D printing can help reduce that. Okay? 3D printing is a process of using a digital file to make three-dimensional solid objects. So you basically have a computer and something that looks like an inkjet printer, and it basically spits out the polymer in a specific array, a specific shape, based upon the computer software, and it layers the polymer one on top of the other until the final object gets produced. It's like watching, Mission Impossible, building the mask that way. That's what 3D printing is, and many schools, high schools, have 3D printers now. In fact, elementary schools now have 3D printers as examples to show youngsters and show people how this technology can be used. 3D printing allows complex shapes to be made with less material than traditional manufacturing processes. And one of the main reasons it allows that is there's no trimming. It also helps the precision, because oftentimes trimming can cause flaws and defects in the final product. 3D printing can help avoid that. An example where 3D printing might be used as dentures, and that's really an area that's really looking at this and really is enjoying the advancements of the science in that area. Okay, but other examples would be eyewear, parts, tools, prosthetics, models. You would start to make your entire movie on your desk. Okay, instead of building a big studio, you 3D print something that really looks cool and looks authentic, and you just do the movie that way. So then you have forensic pathology models and things of that nature. So some really good applications that are coming down the pike for manufacturing processes to help go green. And that does it for this chapter of Introductory Concepts in Polymer Chemistry.